Long before USB drives and cloud storage, Unix systems saved backups to magnetic tape drives. To write an entire directory tree to a single tape reel, you needed a tool that could concatenate files, remember which path each one came from, and restore the layout exactly. That tool is tar, short for tape archiver. A common misconception. People see a .tar file and assume tar compresses. It doesn't. Tar is a streamer. It reads each file and writes a small header plus the file's raw bytes into one continuous output stream. Add up the original file sizes, add a tiny bit of overhead for those headers, and you get roughly the size of the tar archive. Archiving and compression are two completely different jobs. Archiving means bundling many files into one container while preserving the directory structure, permissions, and metadata. That's tar. Compression means reducing file size using mathematical algorithms like gzip, bzip2, or xc. Tar-pux. Compressors squish. Different tools, different missions. The traditional Unix way combines both tools through a pipeline. Tar writes its archive to standard output. That dash means stout, and pipes it directly into gzip, which reads from standard input and writes the compressed result to a file. The output becomes out.tar.gz. Modern tar has a shortcut. It can invoke the compressor internally using a single flag, saving you the pipeline. Modern tar exposes 3 flag shortcuts for the 3 most common compressors. The Z flag calls gzip, producing .tar.gz files. It's the fastest option with moderate compression. The J flag calls bzip2, producing .tar.bz2 files. It's slower but achieves a better compression ratio. The J flag calls xc, producing .tar.xc files. It's the slowest of the 3 but delivers the best compression ratio. Pick gzip when you want speed and universal compatibility. Every Unix-like system on Earth supports it, and it's perfect for quick backups and everyday transfers. Pick bzip2 when you're on older systems that need a better ratio than gzip, but don't yet have xc available. Pick xc when you need maximum compression on large archives and have the time to let it run. It's the modern default for distributing software source code. Welcome to this hands-on demonstration on Linux tar archives. We'll create both gzip and bzip2 compressed archives, compare their output sizes, and then inspect what's inside each one. Make sure you have a terminal open. Let's get started. First, we navigate to /tmp and create a dedicated working directory called tardemo so our files stay isolated from the rest of the file system. The chain cd at the end ensures we land inside the new directory, and the prompt updates to confirm our new location. Now we create 2 simple text files using echo and output redirection. The a.txt file contains hello world, and b.txt contains demo data. Just enough content to demonstrate the archiving process. Here we create our first archive using the Z flag, which invokes gzip compression. The C flag creates a new archive, Z applies gzip, and F specifies the output file name, bundling both a.txt and b.txt into out.tar.gz. Next, we create a second archive using the J flag, which invokes bzip2 compression instead. bzip2 typically produces smaller files than gzip, but takes slightly longer to compress, making it ideal when archive size matters more than speed. Now let's list both archives with a LA to compare their sizes side by side. You can see out.tar.gz is 132 bytes while out.tar.bz2 is 138 bytes. On tiny files like these, bzip2 overhead can make it slightly larger, but on real-world data bzip2 typically wins on compression ratio. Finally, we inspect the contents of the gzip archive using tar.tzf, which lists every file inside without extracting anything. The T flag lists, Z tells tar the archive is gzip compressed, and F specifies the file. You can see both a.txt and b.txt are preserved inside, ready to be extracted anywhere. Imagine a small factory with 2 rooms. In the first room, a worker called tar bundles your files into a single neat box. That worker doesn't know how to shrink the box at all. In the second room lives a compressor, like gzip, whose only job is to squeeze boxes smaller. The 2 rooms are connected by a conveyor belt, a pipe. Whenever tar finishes taping a box, it slides onto the belt, rolls into gzip's room, and comes out the other side squished flat. Now here's the secret of the whole system. The command tar with the Z flag isn't doing the compression itself. It's really just setting up that conveyor belt for you behind the scenes. The Z is a polite request that says, please, run the compressor on my behalf. The belt, the worker, and the machine are exactly the same, only the typing is shorter. Why does this matter to you, the user? Because if you understand that tar and gzip are really 2 independent programs passing data through a pipe, you can mix and match them however you want. You can send the squished box across the internet, into another program, or wherever a pipe leads. The flags are convenient labels, not magic. Let's look at the actual commands. The first line is what most people type. Tar with the C flag to create, Z to compress with gzip, F to name the file, and the output file name out.tar.gz. It looks like a single self-contained operation, but it's really a wrapper. The next two lines reveal what's really happening underneath. tar writes its archive to a dash, which in Unix means standard output, the open pipe. A vertical bar, the pipe operator, hands that stream to gzip. Then the greater than sign redirects gzip's output into the file out.tar.gz. This is the manual form of the previous line. Same result, no hidden plumbing. Once you see the manual pipeline, you can extend it. Here we take the same idea and add another stage. Pipe the compressed data through SSH, which securely sends it to a remote machine. There, the receiving shell writes it to backup.tar.gz. No special network flag on tar, just chaining pipes, which is the entire Unix philosophy of small tools combined together. You don't have to save to a file at all. Here, tar writes the compressed archive straight to standard output, and another program reads it. This is how installers and package managers often consume archives, by streaming them directly into memory or another tool. The pattern is always the same. A tar stage, a compressor stage, and whatever comes next. Now the three compressor flags and their matching extract flags. The C is replaced by X for extract. The Z corresponds to gzip, the J to bzip2, and the capital J to xc. So the same pipeline logic runs in reverse. Gzip, bzip2, or xc decompresses the stream, and tar pulls files back out of it. Many modern versions of tar even auto-detect which compressor was used, so you can often just use X with the file, and let it figure out the rest. Each compressor is a different trade-off. Gzip is the speed demon. Cheap on your CPU, around 3:1 compression, and supported everywhere. bzip2 is older and slower, about twice the CPU cost of gzip, but it squeezes files about 10% tighter. XC is the modern champion. 5 to 10 times the CPU work of gzip, but roughly 30% better compression, which is why Linux distributions ship their source tarballs as .tar.xc. And here's the final bit of wisdom, the kind that saves you CPU cycles for nothing. If your files are already compressed, JPEGs, MP4 videos, MP3 audio, zip archives, running them through gzip, bzip2, or XC will burn your processor and gain you almost zero space. There's no hidden pattern left to find. So pick the compressor that matches your data. XC for source code and text, gzip for quick backups where speed matters, and skip compression entirely for things that are already squished.